I'm trying to get this resolved, but I had my first false positive on YouTube Tuesday. YouTube sent me an email. Did I tell you guys about this? YouTube sent me an email saying one of your videos you uploaded, it was called the Binomial Distribution, and I don't know if it was for you guys or for the other class, contained a spider, robot, or other web crawling device. And I'm like, okay, it didn't, because I uploaded 706 of these things all the exact same way. I dump from my camera to my computer, upload to the server, call it good. So I did an appeal form. They took the video down. So if anybody was trying to find that video, I have to somehow re-upload it. I have no idea how I'm going to do that because I trashed the original. So anyway, I sent an appeal form in and said, there's no spider, I don't know what the hell those things are anyway. They're not in my video. And then they sent me a note back saying that, oh, it means that you uploaded a program with your video that basically what they're insinuating I did was I am forcing people to come to the video by using artificial means. Oh. So robots being clicks. Well, number one, the video is not monetized, so I have no incentive to do that. It's one thing if I monetize the video, which I don't do because that's annoying for you guys. Having an ad pop up every time you want to watch a video, that's annoying. Because if I did that, I could see they have a point, but they're just videos that like 5 people watch. And it's funny because they said you can't upload any devices that allow more clicks in a given time period than a human being. And I checked all the videos around it, 1 view each. It's like, unless that person's moving through molasses, I'm pretty sure I can click once in 3 or 4 days. Pretty sure. So the problem with it all is that they said if you're found in infraction of this a second time, we'll suspend your account. And that's when I got nervous because I'm like, oh no, no, you will not, because we have an entire class based on this. So I'm working through the details on that one. I'm trying to get them to admit it was a false positive, but because they're YouTube, they're smarter than me. Right. Except they're not, but that's okay. I'll find you.
Yeah, you're a done deal now, man.
So, anyway, we'll figure it out. It might be the kind of thing where I have to make a new account every term. I don't want to have to do that. It's annoying. But I also don't want to get locked out. Now, every 700, I mean, if we approximate this as a probability, it's binomial, with 1 in 706 chance that I get flagged as false positive. This ties, just so you know, this ties in beautifully to your last project, which is false positives, false negatives. So God only knows how many false negatives I've got because I wouldn't find out about them through YouTube. They wouldn't flag a false negative. They wouldn't say, "Oh, we think you're uploading spam." Oh, never mind, you're not. That would be the guy who was not getting caught. That's not me. I'm the guy who's not getting caught, the guy's not uploading it, getting said that I did. So I just tested positive for Lyme disease again, essentially, even though I don't have it. So anyway, I'll resolve it. It won't affect you guys, I don't think. At least if 1 in 706 probability is pretty unlikely. But it's still likely enough when I upload 10 videos a day. It's every 70 days I'm going to get flagged for spam, and if they shut my account down, it pisses me off. So, anyway, we'll figure it out. Just want to let you guys know if you can't find one of the videos, that's what happened to it. But it sounds like only one person wants it anyway, so if you're in here, I apologize. All right. So, today! Yes, today. Today we get into the normal distribution, part the second, which is when we actually start applying it to things, as opposed to just playing with technology, which we did last time. Yes, we played with the normal, I believe. We were playing with the normal. Yes, that was great. And we need that. We need the normal. We like the normal. We like that because it gives us a baseline to work off of.
Let's just go over a couple times still normal, won't we?
Oh, we're going to use it every single time. Okay. Oh, Tiffany, yes, we use it every single time we do a normal problem. We have to revert back to normal. The reason we need it, let me just show you what I'm talking about here. I'll give you an example as to why we need this conversion to these things called z-scores. You know what? No, I won't show you that yet. We'll come back to this. But yes, we will use it every single time. I won't give you a chance not to get used to it. So the idea is, you've got this bell curve. And STA normal stands for standard normal. And when it's standard, what number do we put in the middle? 0, by definition. By definition, 0 is the average. Which means if you're at average, you're at 0. What's the standard deviation of this thing, numerically? Do you remember? Yeah, I'll give you the answer right here. It's 1. Exactly, Nick. It's 1. So if you go 1 unit either direction, -1 to 1, that's 1 standard deviation. Negative 2 to 2 is 2, so forth and so on. Off to infinity. It goes forever, technically speaking. And that's great, as long as you're dealing with data that has an average of 0 and a standard deviation of 1. Can anybody think of anything that has an average of 0 and a standard deviation of 1? I can't. Because nothing, I mean, you can see, like, things can have an average of 0. Like, for example, if you think a diet's not working, if you think that, save your money, that diet's not going to work anyway, well then your average weight change over the course of a diet should have an average of 0. Because on average it should cancel each other out, but then nobody can claim that it also has to have a standard deviation of 1 pound. I mean, that's kind of brazen. I mean, it could be 0 pounds, it might be 5 or 6 pounds. So the trick with the standard normal distribution is you don't have flexibility to actually answer real world problems with it. And that's where today we bring in what's called the general normal distribution. And what's cool about this is, Tiffany, to answer your question, it always goes back to the standard normal curve when we're done. But we have to start in the real world of things with units. No, there's no units up here. It's 0 in the middle. 0, 0. Not 0 inches, not 0 feet, just 0. The real world has units. Things like baby weights. You know, things like temperatures of rooms. Things like that. I mean, I just got a text from a friend who had their baby 6 weeks early. Right, exactly. I freaked out. Because it was bizarre because I'm analyzing that with you guys today is short and long births as far as gestation periods. We're going to analyze that. Turns out they're bell-shaped, but they don't have an average of 0, standard deviation of 1. They've got different averages of standard deviation. So what's cool about this is this guy up here has an average of 0 and a standard deviation of 1. That's a standard deviation. Pretend that's kind of horizontal. Not like a sword fighter. The general normal has any average it has any standard deviation it has. And you have to know those things before you begin them. And that's the beautiful part. You'll know when something is normal, because I'll tell you it's normal, and it's got an average of this and a standard deviation of this. So I want to start by picking up where we left off last time, which was, what was the last question I asked you in class? Do you remember? Have you ever called anybody a moron? Idiot? Imbecile. What were we talking about? Remember? IQ. That's what I want to talk about. I want to talk about IQ today. We'll start. We'll talk about IQ, and then we'll talk about pregnancy lengths, and then we'll talk about Michael Phelps and Mark Spitz. And that'll all tie together. I promise at the end of the day, they'll all tie together. It's like, okay, dude. So, first, IQ. This is the definition, well, I'm not saying anything. IQ is defined to have an average of 100. Do you remember why the average was 100 for IQ? Do we talk about why? What does IQ stand for?
Intelligence quotient.
Intelligence quotient. And how do you form that quotient? Which two numbers are you quotienting? Good! Mental age, real age. Mental age over chronological age. If they're the same, that's a 1-to-1 ratio. Times 100 is 100. That's why average is 100. You're just as smart. No. You're just as intelligent as your body says you are. Madeline, go.
Which is why if you take IQ at a younger age, it's likely to be higher than if you take it at an older age.
Bing! Exactly right. A 2-year-old that tests as a 3-year-old, which is not that hard to believe, precocious 2-year-olds, they have an IQ of 150. Because 3 divided by 2 is 1.5 times 100 is 100. 150 is off the charts. You're about to see why it's off the charts. Because this doesn't tell us it's off the charts. It just tells us it's 50 points away from average.
150 isn't off the charts. It's the top, like, 5%, isn't it?
But that's off the charts.
Oh, okay.
If you talk about what people call, when they talk about off the charts, 95th percentile and past is considered off the charts. And watch this. Thank you for that, by the way. This is the measure. That's the measure that tells you how impressive 150 should be. If the standard deviation tells you how, the middle, the 100 is only one piece of the puzzle. If the standard deviation for IQ is also 100, then 150 is like, whatever, that's just a little bit above 100. But the standard deviation for IQ is 15 points. These are both in what are called IQ points. I don't exactly know what they are. So now what I want to do is I want to add a secondary scale under this one so you can see how they line up. So Tiffany, to answer your question, I'm going to keep answering your question if you don't mind. We're going to line up these numbers under those numbers and show you the back and forth conversion. Because what Tiffany has hit upon is what we have to do today is go back and forth. I gave you a program called Still Normal. I did not give you a program called GNormal for general normal, and that's because I want you to get used to the conversions, because most of 244 deals with those conversions all the time. There's even less math in 244 than 243, believe it or not. I know it's kind of hard to believe. There's just very little math in this class. But the math that is there does contain quite a bit of this conversion back and forth. So instead of 0, we're going to have
100.
100. Instead of 1, what's going to be out there under 1?
15.
115, yes?
Oh,
right.
We're going to add the 15 to the average. Just like it's always mu plus a sigma or 2 sigmas or 3 sigmas. So you've got to go up on the scale so it's 115. So you've got all those numbers between 100 and 115. Let me check, make sure I hit record. I did. Okay. We can see everything. Yes. And then at 2 standard deviations,
130.
130. And at 3 standard deviations,
145.
145. And you can see now why I'm referring to 150 as off the charts.
Yeah.
It's past 3 standard deviations. So you know that's pretty rare. Because how much data is within 3 standard deviations? Roughly.
95%.
Way more than that. 99.7% is 3. 2 standard deviations is 95.
Okay.
You're getting almost 90, almost 100 within 3. And this little kid's score is above that. So he's in the top 1 of 2,000 or 3,000 as far as IQ goes. What does that mean? I have no idea. I don't know what it means. I don't know what it measures, but I know he's got a high IQ by this scale. And we can go this way too, right? We can go down 15 to 85, then to 70, and then to 55. And technically speaking, this keeps going forever. But I mean, there's going to be a limit, a realistic limit. You can't have negative IQ. Well, I don't know. Maybe you can. But by the definition of IQ, you can't. You can't go to a mental age of negative. You can go to 0, theoretically, I guess. So although this curve does infinitely go on forever because it's exponential in nature, realistically it tapers off at 0. And realistically, there comes a point when you can't. I think the highest IQ on record, we looked it up, didn't we?
Yes.
Marilyn Vos Savant was like 220 or something, or
Higher than that.
higher 230. It was very high, right?
Ridiculous, yeah.
Very high, which would be kind of like a 2-year-old testing like a 4.5-year-old. If you think about it, a 2-year-old testing like a 4.5-year-old is a 250 IQ, right? 4.5 divided by 2, that's 225. Regardless, it's pretty high. So, and again, it's not that hard to believe with a little kid. I mean, how many of you have met a 2-year-old kid that's precocious enough you could pass off for a 4-year-old kid? It doesn't. I mean, maybe a 2-year-old passing off as an 8-year-old is a little bit of a stretch, but they happen. They call them prodigies. And they may have IQs that are 800 at that point, which they would have, right? An 8-year-old, or a 1-year-old as an 8-year-old, or a 2-year-old as an 8-year-old be a 400 IQ. You never hear about those. That's because they don't get tested necessarily. Plus, who knows what it talks about anyway. So anyway, there are the cutoffs. So you know right away that 50% of people have IQs that are less than
100.
100, 50 have an IQs that are greater than 100. You know off the bat that roughly 2/3 of people have IQs between 85 and 115. Roughly 95% of people have IQs between 70 and 130. Almost all of them are between 55 and 145. And this is where these numbers come in handy. That's why I asked you about moron, imbecile, and idiot. Each of these numbers corresponded to one of those back in the day.
Right.
If your IQ fell down far enough and you hit one of those numbers, then you were in the moron range, or the idiot range, or the imbecile range. Right? Now just our closest friends are in those ranges. So what
It was a technical term.
It's a technical. It was a technical. It was a university psychological term. Exactly right. And they've changed. Precocious was used. I think precocious was above 145 for years. That was back in the 30s. Precocious. I mean, we use that word in a positive way. I used it 3 times today. Little precocious kid. I love that word. But that was an IQ term. Precocious means above the mental age is above the chronological age. So anyway, let's talk about one of the more PC terms that have arisen out of all of this. Dull normal. Dull normal. George Carlin had a field day with this where he's still alive. Dull normal. What do you think dull normal is? Where do you think dull normal is?
85.
Good. So we're left of 100. So the word normal gives you an idea of roughly average. But dull gives you the very PC, watered down, flaccid view of that it's a little bit south of normal as far as IQ goes. The definition that dull normal is they have an IQ that's bigger than 80 but less than 90. As you said, 85 is right in the middle of it, Madeline. 80 to 90 is your range of dull normal. And you got to remember that these ranges change quite a bit. I mean, researchers are constantly, if you go through the history of IQ scales in Wikipedia, it's like this long. Because people get upset with terms like moron because they become part of lexicon, they have to change them. And then they can't have things like genius because then people get stigmatized like, oh, your kid's a genius. So they have to keep changing the terms. So dull normal seems to be one that's stuck. Danny?
Here's my question. Why do they even have to give it a name?
I don't know.
Say
he's got this IQ. I don't. Danny, humans like to compartmentalize, I guess.
Because it's like...
Same reason our pants have pockets, I guess. I mean, I don't know. We like to put things in places. I'm guessing.
It's just like, even dull normal is like, oh yeah, I'm going...
But as soon as you compartmentalize, you've got a point though. Because as soon as you compartmentalize, by definition, you've called it this, right? I told you this. If you look at BMI, come off IQ for a second. BMI. I am this close to overweight on BMI, a BMI scale. That close. Why? Because they've defined the range of BMI to be this wide, and I'm at this end of it. Secondary why? Because BMI is an incomplete measure of health. It takes height and it takes weight. A really dense person is going to be heavier than they should be for their height, and that's where I fall. So as soon as you compartmentalize, it might make certain things easier, but it also makes things less precise and less useful, in my opinion. Good question. I'm going to answer for you. But we can quantify it. That's the best part of this. We can actually quantify these things. That's what I like about it. So that way, when you have a discussion with someone like a psychologist, you can bring this out and be like, but if you've defined this % of people as dull normal, I mean, isn't that a stigma? Isn't that are you stigmatizing the population by that? And just see how they kind of swerve under that. It's, if they give you a number, you can quantify it. And it's amazing. As soon as you start, that's why I can't wait to hear what YouTube comes back when I say, well, I got 1 in 706 flagged as a false positive. That's a pretty low false positive rate. But I'm concerned because I upload 10 per day. That means on average, 17 more days you're going to flag me again and pull my account down. I'm curious to see. There are smart people that work there. I'm curious to see how they respond to that. So we'll find out. Whenever you can quantify something in a way, even if it's off a measure that's a little bit suspect, at least you can quantify it and have a discussion about it. And it's amazing because you can tell the people that don't want to actually think about it, they'll back away and be like, they'll give you a lot of generalizations. Then keep pressing, keep pressing. So you're learning in this class, critical thinking. Not much math, but a ton of critical thinking. Hey, speaking of which, how many people, what % of people are dull normal? If you had to guess, what would you say? If you had to guess, what would you say?
60-something.
60-something. 40-something. 40-something. Good. I'm going to put something at the
I'm
end.
going to say about 33 because you said that one standard deviation was 2/3 of the people, which means that half of that 2/3 goes on one side and half goes on the
So
other.
check it out. We have this curve. So all we've got to do, let me use some more color here. We can actually, we know it's got to be less than 50%. We know that, yeah? And here's why. Think about the curve. Here's 85, here's 100, here's 70. 80's here, and 90's here. So 90 is going to occupy a place up on this curve. And 80 is also going to occupy a place up on this curve. So essentially what we have to do is figure that area out right there. That's our job. Now the problem is you can't use the normal to do this because if you go into the normal and enter 80 and 90, if you do it as a forward between problem, it's going to give you an answer. And the answer is going to be wrong because when you type in 80 in the normal, what does it think you mean? 80 what?
Percent?
No, it doesn't mean, if you're going forwards, it doesn't think you mean 80. 1, 2, 3, 4, 5. 80 standard deviations, which is ridiculously off the charts. That's a 1-year-old testing as an 80-year-old, which I have no idea what that even means. No idea what that even means. But so you have to, what you have to do, exactly. What you have to do is you have to normalize or standardize the value of 80 and 90 so that it fits on this curve. Can anybody think about what the numbers should be? Madeline got us started over there. She's damn close. What would 90, let me ask this first a question. What kind of number should 90 be? Positive, negative, or 0?
Negative.
It's got to be negative because it's left of average. So Patrick, what are you thinking? What should 90 be?
Negative half and...
Damn close. Negative half and negative 1.5?
Yeah.
Damn close. You're saying half, and I like what you're saying because it's between this and this, but it's not directly between them, is it? Look at it again. 85 to 100 is a span of 15, correct?
Yeah.
This distance is a span of 5. That means this distance is a span of 10. So this should actually be about 1/3 away from -1, or about -2/3. Does that make sense?
Yeah.
And then this one is about 1/3 this way, so it should be -4/3. So -2/3, -4/3. As I'm looking around the room, I'm seeing some panic looks. Because all of a sudden I got talk about not doing any math, and all of a sudden I'm doing a lot of math. Fractions. But it's not that bad. Patrick's like, yeah, that kind of hurt. That was worse than quarter-mile burpees. Or nothing's worse than that. So there is, remember how I promised you guys I would hide from you every possible formula you in this class I possibly can? Here's the second one for the year. The average was the first. This formula is actually so useful and so simple that I think it's worth using. You just did it, by the way, FYI, you just did it. When you said, well, this is 5, that means it's a third of the way up from here or 2/3 of the way down from here. You were doing the formula in your head, but you weren't doing it in a very arithmetic order. So here's the formula we need. I'm going to swing this over here. Keep this on the... It's called a z-score formula. If you need a z-score, and you have what I like to call a raw score, I'm going to call it x, because we tend to use random variables as x a lot in this class. I like that we keep with that tradition. So x would be any of these values on the IQ scale. If you've got an x and you need a z, think about what you guys just did. The first thing that you did was you subtracted the average from that x to see how far away it was. Gesundheit. So you figured out, okay, 90's down from 100, so it's 10 points south, so it's negative. So you figured that out. 80's 20 points south, and it's negative. And then you weighted that with the standard deviation. That's it. It's freaking awesome. It's freaking awesome. It's that simple. It's gorgeous, and it's beautiful. As a matter of fact, it's so simple, I didn't believe it when I was taught this years ago by my profs at 371. They said, and then when you're done, if you take the entire data set and normalize, this is called standardizing or normalizing a data set. So you get everything. Now you're on Tiffany, you're on the normal. And his claim, my prof's claim, Vince LaRisha, I love you, Vince, said, now all your data points will have an average of 0 and a standard deviation of 1. And I was like, can you prove that? He's like, sure. And he stood there. I'm like, now? And he's like, we don't have time. And I was like, that's kind of a cop-out. So I went home and proved it myself. And actually, it's extraordinarily quick. If you're interested in why, I uploaded it on the Richmond page. There's a neat little proof. It takes 2 pages, 1 page for each side. 1 page to prove the average is 0, 1 page to prove the standard deviation is 1. It's actually very, very, very slick why it works. But you can trust me that it works. Trust me, if you want more, read the proof. I was fascinated and satisfied by that. I prove everything that I say in class, like this formula works because of this, and this is because of this. I proved all that stuff online for you, if you're interested. Or if you can't fall asleep at night, that could probably knock you right out. But the idea is that all this stuff is valid, and this fascinated me. As soon as you convert x, because remember, x has an average of 100 at a standard deviation of 15. When you do this to the random variables, it now has an average of 0 and a standard deviation of 1, which means we can use the normal and be happy. Cool. So let's do that. Let's do that. Let's take each of those little raw scores of 80 and 90 and normalize them. Yeah, there you go. So if we normalize 80, we take the raw score of 80, dump the average of 100 minus 100, divided by 15. And this is going to sound familiar to you really quickly. It's negative 20/15ths, which if you recall, we were calling negative 4/3. It's 4/3 of the way down from average. Yeah. And 90's 2/3 of the way down from average. 90 minus 100, 15. It's negative 10/15ths or negative 2/3. So essentially, you have to figure out what percentage of people live in the space between negative 2/3, that different color, and negative 4/3. So here's negative 4/3 right here. Go ahead, Madeline. No, ask me. Ask me.
Isn't that negative 2?
Is it what, negative 2?
So negative 4 and negative 2, like, are you saying that we're adding those together?
No. I'm saying those are the z-scores now that are up on this axis. So this becomes a forward speed. No, careful. No. What we're doing is, remember on Monday, we had set up boundaries for a shade. These are our boundaries for the shade.
Okay.
So what we're gonna do essentially is, what's the chance they're at negative 4/3? What's the chance they're just to the right of negative 4/3? Which would be an IQ of just higher than 80, then just higher than that, then just higher than that, and keep doing that until we get to 90, which occupies the space of negative 2. So basically, you're gonna shade this entire region and add all those shades up. You know, the numbers themselves are never averaged. That's a good question, actually. You never actually average the z-scores. The z-scores, like standard deviations, are only locations on the line to tell you how spread out things are.
Got it.
What you average is up above. This stuff in the P of X. Averaging, I'm glad you're saying this, actually. Averaging these values would be like, this is a really good point you bring up. Remember in the olden days of X and P of X? Mm-hmm. Averaging these values would be like averaging these and ignoring these.
Oh, whoops.
And that's what, right, you can't. You have to tie everything together. Exactly, my friend. So that's why you want to look up here. And when I say look up here, this is what technology is doing for us. Because we can't do that without calculus. And we're not doing calculus anymore. So go to normal. Now, Tiffany, here we go. Request granted. Yes. I need to go to normal now. I need to plug this thing in now.
Which button? Sorry.
Program. I don't know how. Say that again. I didn't hear you. I'm sorry.
There we
Go.
go.
Let me swing that sideways a smidge.
What's
that?
We were talking about the graph.
Oh, yay. That was good. Okay. Well, thank you. So I'm going to come over here. We'll get rid of this temporarily. I do want to make a reference to that again. We can leave that there, I think. So yeah, we're under program. Go find normal. This is definitely a forwards problem. Do you remember what makes a problem forwards versus backwards? You will not forget this by the end of the day, I promise you that. But do you remember what makes it forwards versus backwards?
No.
That's okay, good, good. No, this is good. I wanted to hear that because that's why I want to talk about it. What makes it forwards? What do you start with?
The average and the...
Good. You start with the numbers on the horizontal axis and you're going after the probabilities on the vertical axis. Good, very nice. We'll recap that in writing soon. Okay, but it is forwards. It's between because we have a left and a right stop. And these are where your bounds go, Madeline, you were asking about. So just make sure you put them in the correct order. -4/3. Yep. And then -2/3. And then it will draw you. There they are. Look, it's exactly where it should be. So, what percentage of people are dull normal? 16%. 16% have IQs between 80 and 90. That's pretty cool. That's pretty cool. It's less than we thought.
Yeah.
Less than we thought, right? Good. Here's a question for you.
Wait a minute.
Go ahead.
Wait. So. So we were saying that once, because it's outside of one standard.
Yeah, now Madeline's bringing up a good point. She's trying to tie all this back to the notion of standard deviations, which is the range of values between. This is why psychology classes drive me nuts sometimes, because they hammer into your guys' heads the 68, 95, 99 rule, which is the 1, 2, and 3 standard deviations. And they make you think that everything has to be in one of those 2 standard deviations. The problem with this is it's offset. It's not, it doesn't cross 0, and things like that. Like, for example, suppose I redefine bright normal, which I think this is actually what bright normal is, as an IQ between 110 and 120. What percentage are bright normal?
Assumably 16.
16%!
Yeah.
Because that's symmetrically opposed with dull normal, yes?
Right.
Good! Now, let's define a new range. Normal normal, which is everybody between bright and dull normal. Who's in there? Who's in there? Now, you don't have to know this.
You just have to figure it out.
You can figure it out with your technology, can't you?
All right.
Because you know this is -4/3, and this is -2/3.
Right, so that's -2/3 to +2/3.
Mm-hmm. Exactly. So these have to be symmetrically, but opposite sign, but the same number.
Wow.
And that number might ring a bell as something we talked about last class. When you run -2/3 to 2/3, who do you find?
50%.
50%. And this is why I brought up, I may have brought this up last class, I know I brought it up with the other class. When they teach you the 1, 2, and 3 standard deviations, they're great. I think they should also teach you 2/3 of a standard deviation, because that's where half of your data is. Half of your data is within 2/3 of a standard deviation, 50%. So then that's kind of cool. 50% of your data is right here, between an IQ of 90 and 110. And then we tack on 16 and 16% more. What's that, 80 and 120? So it's 32 plus 50, so 82% of people have IQs between 80 and 120. That's the beauty of standard deviations, is you can then get a cumulative sum, Madeline, as you go out from center. That's the problem with the 1, 2, and 3 standard deviations. They force you into too rigid of a framework of understanding what those percentages are. I mean, they're helpful, they're not bad. It's just that we want everything to be that way then. And the trick with that is that's not always the way it works.
Right.
For example, nursing students, you guys have to score in a certain percentage to get in on a TEAS exam to get admitted to the nursing program at ZOCC. Well, that's not a confidence interval. That's the top level of if you graph all the exam scores, you have to be in the top. We're going to answer a question like that next here in a minute. But so it's not a standard deviation in that it's actually an end of the curve, not the middle of the curve. So that's why I like spending about a week doing this in class with you guys, because we can actually analyze it as the whole instead of just one part of it. Does that make sense? You guys buying that? Ish? It all comes back to standard, just the normal. Always does.
Okay.
Now, what I'd like to do on this sideboard over here is give you a kind of a, Renee, when I asked what a forwards problem is, you said you start with Z and go to area. What I want to do is I want to build that out even more to start from the general normal, if that's okay with you guys, because the general normal is more useful. We need the normal, of course. That's where we get our areas from. But we're going to start in the world of units and things like that. So I want to make a 3-step plan for a forwards problem and slap it over here on the board. And we'll also have a 3-step plan for a backwards problem. And we'll do one of those next. Okay? So, for a forwards problem, once you've identified it as such. Now, think about what Renee said. She said, you know it's a forwards problem when you have a z-score and you're looking for a percentage or an area. Perfect.
Which means you have to have the data.
Excellent. Which means to have it a general normal, you have to have the data, the raw scores, or the X scores. So you have to see like an IQ score, something like an 80, or a 90, or a 120. You have to be given data, and the question will be asking you, what is the probability, or what is the percentage? So you will not have the percentage, but you will have the data. Thank you. So you have data, and you want a percentage. That's the definition of a forwards problem. Same for stud normal. Have Z, want percentage. Except now we have one more step to do. Fair enough? So the first thing you have to do is identify that data. Identify the data. Pick the data out. Personally, what I like to do, I like to always draw a curve like this with the standard normal curve plus the general normal that I'm creating from the data, and then slap my data points on there so I know roughly where they are. That way when I runs to normal, I can check my graph that I have there with this and like, oh, they're in the same place. I must have done it right, at least arguably correctly. So this is personal preference. I mean, I wrote the program to draw the curve so you don't have to, but it's also a nice way when you're learning to kind of line them up like that. Once you have the data, that's fantastic. You've slapped it on the curve and you're like, okay, what did we do after we had the data and identify where it was? What did we do next? Do you remember? We converted it to a z-score. Perfect. You convert it to a z-score using this beautiful formula, which of course I will supply for you on your exam. I do not want you memorizing this stuff. Memorizing for the birds. Where does phrase come from? For the birds. That's for the birds.
Leftover food from peasants in France. I'm sorry. My mom's a history major.
That was fantastic. That was freaking fantastic. Wow. For the birds, that makes perfect sense. And then once you have the z-scores, runs to normal, as Tiffany said. Before you said the thing about peasants and the birds in France. Then you just runs to normal.
And it'll be the forward one we're choosing.
These will always be forwards, yeah. These are going to be forwards problems. You're going to pick forward. Then you just have to figure out are you going left, right, or between. Yeah. And that'll be obvious. You'll always go between if you have 2. And you'll always go left or right if you have 1.
Wait, between if I have 2.
Mm-hmm. And we'll see one of the one-sided ones momentarily. If I give you 2 scores like this one, between 80 and 90, you know it's going to be between those 2. But sometimes, as we'll see with the human pregnancy one we'll do momentarily, you have to go to one side or the other. And that'll be a left or a right. But we'll figure that out when we get to it. So runs to normal to get your percentage. Yay! That's a nice template for solving forwards problems. Every single one is solved that way. Every single one. Renee, go!
Do you have
You don't have to. And that's a great question. This is a fantastic question. She asked, do you have to run 1 bar stats to get the average of the standard deviation? No, I give them to you. Because you could never construct the 1 bar stats table for this data because it's continuous.
Oh, okay.
You'd be lifting infinitely many values, which you'd run out of time and patience and life before you were done. So I would never ask you to do it. So this is, and that Renee brings up an interesting point in that these normal distributed data sets, I call them mu and sigma, but they're really not. They're just collected data that's been collected over 10,000, 100,000 trials, and they're calling it mu. They're saying the average IQ is 100 because we've defined it to be that way, and that's what we see over and over again on these IQ tests. Doesn't mean it's mu, it means that we're calling it that way. Just like I tell you in 244, when I have you run Project 3, I tell you the average weight for, I think it's a 2-year-old white American male is, or no, a newborn white American male is 7.67 pounds. That's what medical doctors say it is, because they tracked a whole bunch of them, and they call it mu. Now that's also constantly in flux. When my friend's baby was born yesterday, that average dipped a little bit, because he was under that weight. But I mean, one baby, when weighted with 500,000 babies, how much is it changing? It's kind of like Max pulling the bird out of the bin, right? At that point, the average is no longer 90%, but it's arguably the same. So that's what we're calling mu and sigma. Does that make sense? That was an over-answered question. I apologize.
And you could have an 11-pound baby that's born in the same minute.
That counters the, oh, yeah. So cool you say that. In 105, just last class, I had the kids rolling dice. We were simulating craps. And the chance of winning at craps on the first roll is 8 in 36, because you have to roll either a 7 or an 11 to win on the first roll. So you ante up, throw the dice, 7 or 11, you win. So what I had them doing is I had them all have a pair of dice. I said, everybody gamble. Boom. Gamble again. Boom. And this one girl, Jordan, kept winning. She kept getting 7s and 11s. Everybody else around said, what the hell? And I'm like, careful. Jordan, we're going to take some of your wins and give them to her, and some of your wins and give them over here. We did the sharing thing. And everybody averaged about 2 or 3 wins per 9, which is what 8 and 36 ends up being. Which is exactly what you said. You take some of the pounds from the overweight kid and give it to the underweight kid. Now, of course, you can't do that legally, or healthily for that matter. The parents of the 11-pound kid get a little upset, chopping body off.
Solomon's baby.
Right, Solomon babies, a Solomon, exactly right. But the idea of average kicks in that way, exactly that way, though. Good connection, good connection. Let's do a backwards problem so you can see how they kind of play out. All right, so let's stick with IQ, then we'll take our 5, and then we'll come back and talk about human pregnancy, and we'll kind of wrap the discussion up. So sticking with IQ, the first one was a forwards problem, dull normal. Let's get off of the scales for a second. I mentioned that TEAS exam before. I like that kind of theme. So I'm not going to use the TEAS exam because the TEAS doesn't use IQ tests. It uses the TEAS, or the nursing program uses TEAS, not IQ. But there is an organization called Mensa. They're called the High IQ Society.
Yep.
High IQ Society, yes. So he's like, okay, this exists. They have offices and stuff.
Wow.
My boyfriend's a Mensa.
Yeah, what's that?
My boyfriend's a Mensa.
There you go. Do you know the requirements for getting in?
You have to have over 150.
And where did that number come from? Actually, if you look at their website, you have to be in the top 2%.
Which is what?
Hold that thought. Of IQ scores.
Top 10%?
Top 2%. Top 2%. It's actually not 150.
Oh, it's not?
It's lower than 150. Well, you're going to see why. It's surprisingly, we'll come back to that.
Oh, that's
150 will do it, but it doesn't have to be 150. So my question is, what is the cutoff score that Mensa says, okay, we got to let you in now?
1/3.
We're 130. Danny?
That's
Do
low.
they have a specific age though? Because it would be different.
That I can find.
Because right now I might test into a higher thing because I'm younger, but maybe when I'm 30,
How about
I'll
me?
show that I'm.
This guy. Geriatric up here.
Oh, jeez.
Exactly. That's the thing. That's the thing. No, I've never seen anything about a minimum age or anything like that. And I take issue with IQ tests anyway because I always score well over 140 on all the ones I take online because they're biased towards math people. Take an IQ test. They're wicked fun. You guys would probably all do really well on them because they're like, here's 3 things. What's the next thing in the sequence?
Yeah.
Like you can figure that out.
Yeah.
I mean, I don't know if it's intelligence. I have no, maybe it is. I don't know what intelligence is measuring. But they're fun. What's the next character in the sequence? You know, Bob has this, Ted has this. How old is Alice? I mean, they're fun. They're puzzles. And if you're good at grammar and if you're good at math, you score high on them. So they're biased in that way. So for whatever they're worth. But the question I have is, if you were to be in Mensa, what's the cutoff score? So in other words, Will 150 do it? Will 130 do it? Will 145 do it? Will 115 do it? So we can get close to this. We can get close to this with the graph we already have. But Mensa obviously has a cutoff that they work off of. So let's figure this out. Ready, friends? Let's figure this out. Let's figure this out. We know that if we score 100, we're not getting into Mensa.
Right, no.
Because we're only in the top 50% at that point. And it's just not high enough. What if we score a 115?
No.
What if we score a 115? Will that do it? No. Nick's saying no. How come? What percentage are we in there? What percentage are we in there? Well, we know that this is 50, yeah? What's this? Let me erase this green out of here.
Well, we said that there was 50% between 90 and 110, so 115 doesn't seem like it would.
It won't.
It won't.
It can't, can it?
No.
Because we know that this is 68%, which means this is 34.
Yeah.
So we got 50 plus 34, that's 84%. We're not high enough yet. What if we tack on 15 more points to get to 130? How about 130? Well, this is getting a slightly bit trickier, yeah? 130 is getting close because we know that's 95%. And whatever's down here in this tail added to that might kick us up to 98. But the problem is this is a very inefficient way of doing this.
Yeah.
By trying to guess at what, I'm limiting it to whole numbers of standard deviations. Now, first of all, I told you this was a backwards problem, right? Mm-hmm. How can you tell?
You said.
Well, how can you tell by... That is a high IQ answer right there. Because you said it was. It's interesting. I'm reading a book right now, and one of the questions is, there's a helicopter pilot lost in Seattle in the fog. And he what does he have? He loses his navigation devices. But he can somehow communicate with this high-rise that's sticking through the fog. And he asks the people in the high-rise, somehow, I forget how he does it, but he goes, "Where am I right now?" Trying to get directions. And the people in the high-rise hold up a sign, "You're in a helicopter." And the guy figures out where he is and can guide by whatever few landmarks he can see to the Seattle-Tacoma airport. And when he gets there, they say, "How did you know where you were?" He's like, "It was a Microsoft building." He's like, "How would you possibly know that?" By saying, "Because I got an answer that was completely correct and completely useless." Which is exactly the information I just gave you, completely useless, because I told you it was backwards. It's a great answer. It's a high IQ answer. Very high IQ answer. How can you tell from the context of the problem it's backwards? I gave you the percentage and I'm asking you for the cutoff IQ score, yes? That's how we know it's backwards, because we're starting with the percentage. So we're starting very, very carefully. Now the problem is I don't exactly know where it is. I'm just going to slap it in the middle because I don't exactly know where it is. That's not going to be right on average. But I'm going to call, oh my goodness, I'm going to call this question mark, because I don't know where it is. But I do know this. What is that?
2%.
Yes, that is 2% of the area right there. That's what I know. And somewhere, in other words, this is the 98th percentile, isn't it? Because I have to have an IQ score that beats 98% of people. At least. I can be up higher. Clearly, we know your 150's in here, Madeline, because 150's past 3 standard deviations. So clearly, your boyfriend's 150 is past that. But the question is, you don't have to be that high. How high do you have to be minimally? And that's what that's going to help us answer.
Well, that's funny, because I took a test years ago where I was at 149, and it said I just missed it.
Oh, no, not at all. Unless they changed the rules, it's possible. It's possible they did. So let's swing over here. What I want to do before we jump into this is let's get a blow-by-blow for figuring out how to do a backwards problem. Because I think what we can do, my pocket has a hole in it. Look at that. What we can do is we can reverse the order here. So for a backwards problem, and please realize, friends, I've made these terms up. They don't actually exist in textbooks. But it's nice because students, when they're learning it, it gives them a nice thing to remember. In a backwards problem, you have the percentage, and you want the data.
Okay.
So the last thing that we did with the forwards problem was we got the percentage. Well, that's what you're going to start with the forwards problem. You're going to start with that percentage. So you're going to start with the percentage. Perfect. So we're there. We're at 2%. The second to last thing we did was we converted to a z-score. Well, we're not going to do that conversion right now. Because from the percentage, remember what we did with the z-score? We ran the z-score through the normal. We're going to run the percentage through the normal to get the z-score. So rather than going z-score to normal percentage, we're going to go percentage to normal z-score. Exactly backwards. So you're going to run the percentage through the normal, through the normal, to get a z. Let's do that. Let's do that for the problem while we're doing it. So what z-score does that correspond to?
2.
So let's run, it's damn close to 2, isn't it? It is pretty darn close. I realized it as I was adding the percentages of 95 plus some changes, close to 99. So, let me kill the lights here. And drop this thing right about here. And we're still looking, that's good. All right, more probs, definitely backwards. Now what's cool about, I set up your program to shade either left or right. You could do this problem either left or right. You could shade to the right and put in 2%, which I will do right now. But that's the same as shading to the left and putting in 98%. Because it gives you the same z-score that cuts off. I'll go to the right though, because that's the kind of the logical way I put it in for you. What percent to the right?
2.